Hello, my name is Santos, and I will present the work called High-Dimensional Multivariate Time Series Recasting using self-organizing maps and fuzzy time series. This work was developed by me and Professor Federico Guimarães from Minds Lab UFMG Brazil and Professor Petrônio Silva from EFNMG Brazil. This is the summary of my presentation. First of all, I will introduce the theme of high-dimensional uh, time series in Internet of Things. And then I will explain what is a fuzzy time series and our proposed method, SOM FTS. Then I will present the computational experiments and conclude. Internet of Things, or IoT, is a network of objects incorporated into sensors, software, and other technologies that aim to exchange data to other devices and systems on the internet. There are many algorithms developed to deal with this data, to help decision-making and learn with the systems. High-dimensional datasets are a big challenge to these algorithms because many of them lose performance in high-dimensional spaces. Solutions in the literature that we can cite is feature and revert techniques and data projections. A time series is a sequence of data acquired on time that we denote by the capital letter Y, and we define an instance of a time series as an element of any n-dimensional data that has a time indexer T. We define a universe of discourse U as the interval between the minimum instance of time series and the maximum instance of the time series. The fuzzy time series approach is defined in that way. We get the numeric time series, then we set the linguistic variable A, and to do that, we set the number of fuzzy sets, then we partition the universe of discourse, then create a fuzzy set for each partition. Then we fuzzify the numeric time series and observe the fuzzy temporal patterns. Then we induce the fuzzy rules, and now we create the fuzzy time series. When we talk about multivariate time series, we need to do this process for each feature of our dataset. And we have an endogenous variable that is a feature of interest of our prediction, and explainable variables that is the other features that can be used to predict the values of the endogenous variable. A fuzzy rule has two sides, like in this example. We have the left-hand side, that is the combination of explainable and or endogenous variable, and the combination of fuzzy sets for each feature, explainable and endogenous variable. And the right hand side is the predictive fuzzy set of the endogenous variable. In the literature, there are many algorithms using embedding spaces to deal with high-dimensional spaces, high-dimensional time series. And for example, we can use self-organizing map that is an unsupervised and iterative embedding method. Self-organized map create mapping between a high-dimensional space D and a low-dimensional space epsilon, also called grid. And we can define the grid size as the range of each dimensional of the grid, of the dimension of our grid. And in the process of training self-organizing map, we keep the topological properties like neighborhood and distance of each instance. And as we can see in the algorithm, in this algorithm, we define the parameter key, that is the dimensional or low dimensional space of our grid, and we use the Gaussian neighborhood function to training the self-organized map. Our proposed method is to join the self-organized map and FTS models. We get a multivariate time series and separate the exogenous variable to reduce these variables into a low dimensional space using self-organizing map. And we get, in this example, we have two embedded space with two dimensions, dimension B and C, and we keep the endogenous variable to build a new data set with just 3 dimensions. So now we can use this reduced data set to other FTS method like WMVFTS. Now I will present our computational experiments. We use a data set called gas sensor array under dynamic gas mixtures available at UCI platform. And in this data set, we have 16 sensors of gas and that acquire data in a frequency of 100 Hertz. And we choose one feature of this data set and analyze that and observe that the system is very slow. We can see here in the autocorrelation graphic that this system has high autocorrelation in many legs. So we decide to subsampling the data set to 1 Hertz frequency. The subsampled data set has 9,000 instances. In our experiments, we use 10,000 epochs to train the self-organizing maps and use a learning rate of 0.01. We vary the grid size using 25 by 25 grid, 35 by 35, 50 by 50, and 100 by 100 grid. Then we make the prediction using WMVFTS and get the statistical results with sliding window method that we separate many windows on our data set and get statistics for the prediction for each window. To implement the experiments, we use PyFTS and Simpson libraries. This is the example of the reduction. This is the original data set, which has many columns. Each column is one sensor. And we choose this column that is the time series of the PGS 2602, that is one sensor. And we get all other columns to reduce with self-organizing map. This is the reduced data set. This is the result. We can see in the blue line the original data, and other lines we can see the prediction of with each reduction. The yellow line is the prediction of 25 by 25 grid. The green line is the 35 by 35, red 50 by 50, and purple 100 by 100. And this is the statistics results. We get the root mean square and mean absolute percentage error to evaluate the performance of the prediction. And we can see that SOM FTS using 100 by 100 grid has very good results. SOM FTS 100 by 100 have RMSE of 19.43 and mean absolute percentage error of 0.0069. We compare these results to other algorithms like MLP regressor that obtain root mean square of 24.14 and mean absolute percentage error of 0.0109, and vector autoregressive with that obtain the RMSE with 789.31 and the mean absolute percentage error of 0.3750. Other result that we observe that is the rules of the FTS models, and we observe that as we increase the grid size, we also increase the number of rules of the FTS model. So we can conclude that SOM FTS is an efficient way to deal with high-dimensional time series, is a nonlinear embedding method, and interpretable. The grid size 100 by 100 achieves superior accuracy, outperforming VAR and MLP. As future work, we can evaluate other embedding and projection techniques, such as PCA and autoencoders.